Yeah, hello everyone out there. And first of all, a warm welcome here on behalf of the EMAG group. Welcome to today's webinar on the topic of high precision machining of rotor shafts for electric drives. My name is Jörg Lohmann. I am head of technology and sales at the business unit Gear Hobbing Soft. And I can look back on a career in gear business of more than 20 years. My colleagues and I are pleased that you have decided to join our webinar today. But before we start straight through, there is still an important organizational note that I would like to make you aware of. Ladies and gentlemen, this is an interactive webinar. That means you attendees on the screens are kindly invited to send us your questions in case you should have any. And you can do this by means of two different ways. Either you use the chat function here in this webinar. In this case, also the other attendees will be able to see your question, or you send it through the questions channel, and then the questions will arrive here anonymous directly on my screen in the studio. All right. In case we should not be able, for what reason soever, to give an appropriate reply to your question, we will do this after the webinar, no later than 2 weeks after today. So, ladies and gentlemen, e-mobility is slowly but surely finding its way onto our roads and, of course, into the metalworking industry. And since the masking noises of the combustion engine are simply not existing in electric drives, the requirements on the workpieces have increased considerably as far as their accuracy in machining is concerned. In the following 45 minutes, we are now going to show you more in detail potential approaches in order to face those challenges. So let's start with this example here. This is a Volkswagen ID.3 that we see in this slide here on the left side. And on the right side, we can see the drive unit. This is the e-drive. It consists of the electric motor on the right side, and on the left side, we have the transmission. And if we dip somewhat deeper into the detail, we can see here the drive structure. So it consists of the rotor shafts. In the middle left side, you can see the rotor. Inside it, there is the rotor shaft we are going to talk about today. Around it, you will find this copper coil. This makes it the rotor. The rotor then sits into the stator. A motor housing covers the whole thing. And then we have a bearing shield that is assembled from the front. And from the rear comes the transmission with a differential and, of course, with its housing. Let's take a look on these different kind of motor shafts that we know. So we have classified this in monolithic rotor shafts. That means they are made of one piece. Those are usually turned, for example, from the bar or, for instance, from sawn pieces. Or alternatively, on the right side of the slide, we have built or joined rotor shafts. These consist usually of at least 2 or even 3 pieces that will be joined with a certain method. Predominantly, we consider laser welding or sometimes also friction welding and thermal joining. Another differentiator among those rotor shafts is the interface to the gearbox or to the transmission. So you can see here once again this e-drive. And on the left side, you can see that we have zoomed more into the detail. And you see that there is an interface between rotor shaft and input shaft. And this interface can be designed in different manners. For example, on the left lower side, we see a joined rotor shaft that has an internal spline. In this case, the rotor shaft has the internal spline and the input shaft has an external spline. And these splines, when we talk about splines, it's not actually considered two meshing gears. It's just splines that make sure we transmit the torque. And this is how the torque can be transferred from the rotor shaft to the input shaft of the transmission. And of course, we can do this also vice versa. It may also be the case that the rotor shaft is made with an external spline, and in this case, the input shaft has an internal spline, of course. And an alternative design to this is shown on the lower right side. This is a rotor shaft where we already have actually the geared section. That means rotor shaft and input shaft is more or less the same thing. Actually, it's one piece, so to speak. When it comes to machining of the rotor shafts, first of all, we should consider which are the final properties of the workpiece we have to machine, because this is what actually determines the potential process chains. So the properties of the final part define how the process chain should look like. Here we have a couple of different potential process chains. Well, we have to say that this is somewhat from the gear machining perspective. It usually always starts with op 10 and 20 turning, then comes usually hobbing. It may be alternatively power skiving, so soft gear machining. Then comes the hardening. There may be a joining process, but not necessarily. Then comes grinding or hard turning or skive turning of the reference datums, the bearing journals, for instance. And then we have a gear finishing process. This can be skiving, that means hard rehobbing. It could be alternatively, depending of course on the accuracy requirements, gear grinding, and depending on the rotor shaft's design, in case we have adjacent shoulders or so, that could lead to interference with tools. We could also have, for example, a honing process. Now we have highlighted one particular process chain, and I invite my colleague here in the studio, Matthias Obst, to explain this a little bit more in detail, please. Matthias.
Okay, thank you, Jörg. Hello to my person. My name is Matthias Obst. I am team leader at the technical sales team in the shaft divisions, working with all kinds of machining. I've worked with precision shaft parts for about 25 years. It's been my passion. Today we want to show a process chain that explains the complete machining of rotor shafts, from soft machining to hard machining. This process gives a high machining processing, good quality and efficient production. We start with an overview of the process steps of soft machining at 4 sequences. First one, we have a pre-machining using a pickup machine. Our VL series covers a wide range of part types. The next step, the OP10, OP20, pre-turning with 4-axis turning machines from our flexible VT modular system. OD and ID are machined to create the reference geometry for the following processes. After this, we come to the gear cutting. Our EMAG Köpfer portfolio machined gear cutting in the soft state. This step lays the foundation for the following hard machining operations. Concluding on soft machining forms the foundation for quality and cost-effective production. Next step are detailed gear machining presented by Jörg and Alex.
Thanks. So let's come back to gear machining, soft machining. I already explained that sometimes we have issues with interference to adjacent shoulders, and I would like to dip here deeper into the detail. So with the design of rotor shafts, there is actually different kinds. Sometimes we have enough sweep out for a tool. Here in this drawing on the right side of the slide, you can see the cross section of a workpiece with a spline, and you can see that at the final position of machining, there is the hob shown, or it could be alternatively, of course, also a grinding wheel in its cross section. And due to the fact that in hobbing and gear grinding, we usually have crossed axes, that means that the symmetry axis of the tool is nearly perpendicular to the symmetry axis of the workpiece, there can be problems with interference, as shown in this sketch. So on the lower left side, we can see how something like this may look like in case a workpiece has been hobbed. This is now an armature shaft from an electric motor. And you see that we have a usable length, and then there is an area that we cannot use. This is the non-usable length, and this is the area of the sweep out where the teeth are not fully outformed. So this section cannot be used. And now it depends on how many millimeters are available for this tool sweep out, and this can determine the machining process we should apply for machining each individual rotor shaft. Here is a very nice slide. We have taken a couple of pictures from the dissertation of Dr. Ruben Bauer from IBU Fraunhofer in Chemnitz. In his dissertation, he made this problem quite clear. On the left side, you see in gray color this workpiece. It has a spline and it also has this adjacent flange or shoulder. And you can see the three different soft machining processes: gear hobbing, gear shaping, and power skiving. And in case of gear hobbing, you can see the problem that I explained a couple of minutes ago. So we have interference between hob and the adjacent shoulder. So this workpiece can simply not be hobbed. So we need an alternative solution. And this can be the gear shaping process. Why shaping? Simply because in shaping, the tool symmetry axis and the workpiece symmetry axis are parallel. Accordingly, we have the smallest possible sweep out we can have. An alternative to this is power skiving. In power skiving, the process kinematics foresees to have an axis crossing angle. This axis crossing angle is usually between 20 to minimum round about 10 degrees. And accordingly, we will also have a way shorter sweep out in comparison to hobbing processes. So on the right side of this slide, we have a very nice categorization of these processes as far as their productivity and flexibility is concerned. So there's the broaching process for machining of internal splines. It's a very quick process. It's a single stroke process. The broaching needle will go through the workpiece to be machined with a single stroke, and the workpiece will be, or the gear will be finished. Then we have the three processes: hobbing, skiving, and shaping. Hobbing is considered to be the most productive, most cost-effective process among these processes. And then comes the skiving process that is considered to be less productive, but with higher flexibility. This is a point where I struggled somewhat, and I would like to ask also my colleague, Alexander Morhardt. So in this categorization, we have the hobbing process. It's considered to be the process with the highest productivity. And we have power skiving that is considered to be the most flexible process, or more flexible in comparison to hobbing. And from my point of view, one can discuss about that. This is the reason why I've introduced now Alexander Morhardt from the business unit, Gear Cutting Hard. Alex, what is your opinion on this issue?
Yeah, I think the skiving process is a little bit more flexible as the hobbing process. This has mainly to do that we can produce external and internal gears with this process. I think from the speed, skiving is not so far away from the hobbing process. When you see how fast we go with the tools through the workpiece, this is maybe nearly the same speed. Only we have the backstroke, which is not doing this, and I think this is the difference between hobbing and skiving operation. Yeah. What is the important thing for rotor shafts, of course, are the generating processes. This means hobbing and generating grinding. These are the two processes which are important for this product, because the number of parts normally is relative high, and especially the design is really an important point. It's not only the hop diameter, it's also the OD of the generating grinding wheel. And here it's better when we can use bigger grinding wheels, because we are dressing these wheels. And so 160 millimeter is a good thing, or maybe a little bit below 120. These are really good things, and make parts cheaper as when these diameter are very small.
So I would say, to summarize, among the processes, hobbing, skiving, and shaping, skiving can be considered more flexible due to the reason that it is possible to machine workpieces that have an adjacent shoulder. We can power skive internal gears and external gears as well. This is not the case with gear hobbing, of course. Therefore, I think one can agree, skiving is probably to be considered more flexible as in comparison to hobbing and broaching. Well, I think shaping does not really play an important role when it comes to machining of rotor shafts. So the processes that have a kinematics of continuous character, such as hobbing and skiving more or less, since we have the backstrokes in between, is probably also considered to be more appropriate for machining of rotor shafts. Now, in this slide, we see the tooth gap of a rotor shaft. Here, module 1.52, 31 teeth. Helix angle is minus 18.5 degrees. That means left-hand helix. Pitch diameter 49.7 millimeters. This is the gear data. And we see the tooth gap in normal section, a typical profile design. And we can see that the hop actually removes, well, 95% of the material, and the hop usually is designed in a manner so that we leave some stock allowance along the involute tooth, and this will then be removed later in the hard fine machining process. This can be generating grinding, it can be skive hopping, or it can also be honing. Here we can see a comparison of the different accuracy classes after each individual process step. So here we see the inspection chart, the first side of the inspection chart from a gear inspectioning machine. We see 3 measured teeth each. On the upper side, you can see the profile, and in the lower side, you can see the lead. And here, after hopping, we have achieved a ISO class 7. This is the ISO standard 1328-1. And then the workpiece goes to hardening, and depending on the kind of hardening process, we have a quality loss. Here it's considerably high. We lose 2 or even 3 classes, so we end up in an ISO class 9 to 10. And after hardening, the workpieces will later be finished ground by generating grinding, and then we will end up in an accuracy class ISO 6 without problems. There is one particular product within the eMAG product portfolio that I would like to highlight, and this is the HLC 150H. With this machine, there's plenty of possibilities to machine rotor shafts. So it is a gear hopping machine, horizontal style, with integrated gantry loader. We can hop rotor shafts with this machine, but we can also skive them. That means, in this case, hard rehobbing. But due to the fact that this machine has a special kind of, machine kinematics, we can use it also for power skiving processes of external gears on rotor shafts. And I'm now going to show you a movie not of a rotor shaft, but from another important workpiece of an e-drive, and this is the stepped pinion. The stepped pinion has 2 different geared sections. One has a smaller one and a larger one. Here you see power skiving of the smaller gear. Now we move over and swivel the head over, shift to the hop, and then we hop the external gear. That means we have the perfectly fitting process for each individual gear. Important is also that these 2 gears have a very precise orientation requirement. That means there is a defined angular position among the 2 geared sections. And due to the fact that we machine both gears in one setup, we have no problems to fulfill this challenging requirement at all. Here you can see the gantry loader. This is a linear gripper for workpieces up to 10 kilograms in diameter, 150 millimeter. There's the swiveling unit that picks up the workpieces from the magazine and presents them to the gantry loader and swivels them afterwards downwards onto a conveyor belt in order to deposit them. Another example, a typical rotor shaft application, is a spline. This is the K160 gear hopping machine, still horizontal style, in long bed execution. That means we can hop workpieces up to a length of 600 millimeters, maximum module 2.5 millimeter. It is also equipped with a gantry loader. It's a high-speed loader, aluminum design, double rotary gripper that takes care of the workpiece handling. So here we are in the work area, and the gantry loader exchanges blank with the finished part with a blank. Now we do hobbing, and as you can see, we have a considerably high feed rate. This is also acceptable in this case, since it is pre-hobbing prior to skiving. So we have permitted a depth of the feed scallop marks of even 10 microns. Here is a chain magazine and a deposit belt and the distributor who picks up the parts from the magazine. Now comes immediately hard fine machining. This is now hard skiving, hard rehobbing of the previously hobbed gear. This requires 2 different profiles as shown before, since we only remove material on the gear's flanks. Here we have a different kind of automation. This customer wanted us to have a chain magazine coming from the front, depositing the parts on the rear. Now comes the auxiliary tool. This is the skiving probe. It's an inductive sensor with a blow-free nozzle that keeps it clean from swarf and dirt. And this is necessary in order to synchronize the hob with the workpiece. So we apply an offset on the C-axis and make sure that we find the tooth gap with the degree of precision that we require in order to make sure we remove material on both flanks in the same way. Here, automation system, 2 chains, and the workpieces will be deposited towards the rear of the machine. Right, so let's come back to the topic process chain. My colleague Matthias is going to show us another example of a process chain that has been realized on eMAG machines. Matthias.
Okay, thank you. Now we will show you an overview of the hard machining process steps at 4 sequences. First thing, induction hardening delivered by a supplier. After hardening, we go in a turning machine, VTC 200 CD, that's a center drive machine. This machine concept allows different finishing operation to be done efficiently. Heat deformations are corrected and the dimensions are made very accurate. Next step, power skiving or gear grinding, dependent of the quality of the shaft. This process enables exact finishing of the gearings. Shape and position are kept very accurate. Last process, the hard machining. Final machining is performance by grinding of the requirement tolerance and surface quality. Concluding on hard machining ensure the final dimensions, surface quality and functionality of the rotor shaft. The next step are detailed hard turning and grinding, presented by Yannick.
High rotational speeds and high torques in electric powertrains, this leads to very tight tolerances, especially with regard to the runout of rotor shafts of the bearing seats and the rotor seats. In this context, the machining in one operation is a big advantage to achieve these tight tolerances and to have a very flexible machine concept. My name is Yannick Röttger. I'm responsible for technology and technical sales in the business unit grinding, and I'd like to introduce you into our answer to this challenge, the complete machining of rotor shafts in one clamping on our machining platform VTC 100 or 200 GT. These machines with vertical spindle layout are designed to manufacture shafts up to a length of 400, respectively 600 millimeter lengths, and a diameter of 100 millimeter, respectively 200 millimeters. In the center of the machine, we have the main spindle on top, means it is protected from grinding dust and from coolant. On the counter side, on the bottom of the machine, we have the NC tailstock, where also the dressing spindle is fixed. On the right side of the machine, you find the 30 kilowatt CBN grinding spindle to perform all the grinding operations on rotor or gear shafts. On the other side, there is the turning turret with the turning tools, with the in-process gauge for the in-process measurement during grinding, and we have the double gripper, which brings the raw parts from the conveyor belt and positions the finished part back on this conveyor belt. Which tasks are done within this machine concept? We have the double gripper on the turning turret to load and unload the parts within a workpiece changing time lower than 10 seconds. We perform the conventional turning operations for shoulders and grooves, and we have a Y-axis to perform also skiving to machine very high material in a short time for the pre-machining of the bearing seats and the machining of the rotor seats. The CBN grinding spindle reuse only to remove the last microns of material to achieve the required surface qualities with regard to their ribological behavior in the bearing contact. On the turning turret, it is also possible to place live tools there to mill grooves and other applications. Here we have a look on the machining of a rotor shaft. We start with the actual positioning by means of a measurement probe. We machine the shoulders in a hard turning process, so we have no problem with grinding burn on the flat surfaces. We machine the groove next to the spline geometry. And then we do the pre-machining of the bearing seats by means of skiving technology. We see very high material removal rates with very less tool wear. And only for the bearing seats and the sealing counterface, where we need very small surface roughness and specific tribological behavior, we perform a grinding process with in-process gauge to achieve the diameter tolerances. On this slide, all the results and the processes sum up. We see we achieve total runouts less than 20 microns with regard to the two bearing seats A and B. We achieve surface roughness lower than 0.3 micron, and this during a cycle time of less than 90 seconds. So I'd like to sum up the advantages of this multifunctional production machine, where we perform various technologies in one clamping. We can do the complete machining with hard turning, skiving and grinding with in-process measurement to achieve the lowest form deviations and very small diameter tolerances. We have a very compact layout, so very less space requirement in the shop floor, and especially the in-process measurement makes the machine capacity very, very good, and we have the possibility to machine different types of workpieces with different lengths, with different diameters, just by means of a change in the NC program without any change in the tool setup. Thank you very much for your attention.
In the case of a built rotor shaft, meaning when the rotor shaft consists of 2 or 3 single components, laser welding is the preferred technology. For laser welding, in many cases, other sub-processes are necessary. So, to get these process chains in the right solution, in the right constellation, is a key factor for the productivity of a system. I'm Konrad Eibel from EMAG Business Unit Lasertech. And I will show you an example of one of our delivered solutions for the mass production of a rotor shaft for passenger cars. The system here is for a 2-piece rotor shaft, and 4 process steps were used, meaning laser cleaning, pressing, preheating, and laser welding. First of all, the parts were brought to the system to a pallet conveyor system, the single components. There they are picked up by a gantry, which brings them first to the laser cleaning machine. The laser cleaning machine has a rotary table. This is in order to assure the shortest non-productive times. Here in the laser cleaning machine, the weld areas of the single components are cleaned from organic substances such as cutting fluids, washing residuals, or, for example, rust preventatives. Then the clean parts are transported to the laser welding machine ELC6. This machine also features a rotary table. Here the single components are on the loading side stacked on each other. This is already the position which is then used for pressing. For this, the rotary table brings the components into the working area, and they are pressed together with a force being applied from the bottom. Right after that, an induction coil is positioned on the workpiece and the weld area is preheated. The parts are preheated to a temperature of just about 400 Celsius. Now, the single parts have tolerances, and now they have also been preheated. So to ensure a welding process in the required tolerances, a seam tracking is necessary. For this, we used our own EMAG Easy Seam system. That means during the weld process, the workpiece is rotating and the weld beam is more or less standing still. However, since we have done a seam tracking right before welding, the weld head will adjust during the weld process live. After the weld process is finished, the parts are transported out to the loading side of the ERC6, and then the gantry brings them back to the pallet conveyor system. So what you see here now is a fully automated system, and everything came from EMAG out of one hand for the customer. Here's another look at the system. Again, OP10 and 60 were load and unload of the pallets. OP20 is the laser cleaning system. OP30 and 60 are done in the laser welding machine ELC6. As I've said, everything came from EMAG, and also this includes the processes. And this is why I want to show here at our facility in Heubach, Germany, we have our laser application center where we have the right equipment and most of all also the right personnel to support the customer with first weld tests, small series pre-production, or also a complete process development. In this case, we offer a technology partnership with our customers, and if this is done right from both sides, everybody can profit from the close cooperation. If there are questions on this, please do not hesitate to contact us. Thank you.
Okay, thank you, Konrad and Yannick. Now we are jumping to the generating grinding process. We are normally using for the rotor shafts a machine called G250. So the maximum diameter here is 250 millimeter. And on this machine, we can do profile and generating grinding. And the advantage of this machine is that it's a flexible and high productive machine. So it's really a good machine for mid-size and high production. And what does it mean? We have a high productive machine. High productive machine means this is coming out of the table group. So we have here an area where we load and unload the part, do the meshing, and then we have an area where we grind the part and then swivel it around after the grinding operation is ready. All other parts can also produce on this machine, all automotive gearboxes, parts for e-drive, or also long shafts up to 700 millimeter. But flexible is more coming out of the grinding head himself. There we have two possibilities. We have a standard grinding head up to 8,500 RPMs, and then we have a high-speed head up to 20,000 RPMs. And there is a tool arbor in the machine, so this direct-driven grinding head, and we have a tool arbor there, and we can mount different kind of grinding wheels, but also we can remove this tool arbor completely and can set a spindle nose in where we can put also very small profile grinding wheels on, for example, when we are making small gears with interference for gear motors, which have a small diameter. So also here the distance between the main axis is only 50 millimeter. With a 30 millimeter wheel, we can grind to zero. And also this machine has the possibility to produce a face width of 380 millimeters, so it's not so important where the wheel is placed in the working area. But let's come back to the generating grinding wheel. So here we have the possibility to use different grinding wheels. The standard wheel can be dressed from 250 millimeter down to 180. Then we have a medium size, 160 down to 120, and a small wheel can be dressed in the outside diameter from 120 to 80. So we are absolutely good prepared to produce rotor shafts, which normally has an interference with these small wheels with a dressable ceramic worm wheel. Which is also necessary. We must produce, of course, a high quality, but also there are sometimes special modification in the gear necessary. So here we have also the mandatory software on this machine. We have bias control software so that we can make modification in the bias and also correct these. And this is very nice on this kind of machine because we have a visualization on the screen, and the operator can look in which direction he do correction, or in general, when he is setting up the machine, he can look directly what is going, what will the machine do without grinding anything. So it's a very fast setup, and also during the process, the correction can be done very easy. Then, of course, we have the possibility to have super finishing on this machine. This can be fine grinding, or this can be also polishing grinding. And, of course, we have a software to make modification in the software surface himself to have a low noise gear at the end. So let's have a look how does it works in the machine. When we have such a rotor shaft for the finishing operation, there are only two possibilities. One is generating grinding and the other one is honing. With the generating grinding, I think we are much cheaper as with the honing process. And especially here on this machine, which is very, very stiff, we can produce this really in a good way. On the photo on the right side, you can see a grinding wheel with the dimension of 120 millimeter in OD. And so here we do this process here on the machine. Also meshing is an important point in this machine. We have this installed on the loading and unloading area, so it works in a similar way as Jörg mentioned before. So we have an inductive sensor. This is here mounted on a retractable arm and can adjust in diameter and also in the height. And it's swiveling in when the workpiece is loaded, and then we do some RPMs and check where the gear is located. And then also here we can do a C correction that we mesh with the grinding wheel directly into the workpiece and remove the same stock on the right and the left flank. This is one possibility, and also there is another one. This is when we didn't have this retractable arm, that we are doing this with 2 NC axis, so that we drive the inductive sensor automatically to the workpiece. Also here it's possible that we also checking the runout of the part with an additional probe here on this automatic meshing unit. And this is necessary also when the setup times must be very short, then we can use this kind of NC axis in the machine. Let's have a look what can we do with this grinding operation in terms of quality. Here, this is a measurement chart after heat treatment. You see here a lot of variation, especially here in the lead direction, and we must compensate this afterwards with a generating grinding process. Here now is the chart after the generating process, and the scale of this measurement chart is 1000 to 1, so you can see everything here. And all the quality items are below DIN 5. And when you see, we have highlighted some criteria here on the right hand, and for example, FF alpha is here 1 micron, and this is not only in profile direction, this is also in lead direction. So this is really a good quality, came out of this stiff machine. This is also a heavy machine with 14 tons, and also some special equipment in the tower where the 2 direct spindle are mounted, so that you can reach this kind of quality or this level of quality very easily. So now I think we jump over to the layout of rotor shaft, and I will give the word back to Matthias. Thanks.
Thank you. Now we will show you an overview of the rotor shaft production station. That's 4 steps. First step, soft machining, robot cell, hard machining, and the quality check. First, we will start on the left side, on the rough part conveyor. We put it manually on the system. Then we see 3 machines, VL8, pickup turning machines, 2 VT4 4-axis shaft machining, link it with a track motion system. They put the part to the operation and set up in the robot cell. The robot take the part from the soft machining, put it in a blow-off station, go to the hardening process. After this, we go switch in the blow-up station and put it in the hard machining line. First one, we have a VTC 200 CD machine, a center drive machine. They're turning the end and pre-turn the belt seat. After this, we have a gantry loader system for the skiving process of the gears and the end finish process in a grinding machine. After this, we have a quality check with a measuring unit, a marking unit, and put a part to the finish part conveyor. Summary and advantage of the rotor shaft complete machining, soft machining, high material removal rate and short machining time, low tool wear and reduction costs, high flexibility in geometry and tolerance, hard machining, very high dimensional and shape, correction of hardness deformations after heat treatment, excellent surface quality. Conclusion, soft machine is cost-effective and flexible. Hard machining gives tight tolerance and quality. Together, they create a reliable and high-performance process marked on complex precision rotor shafts. Now you see there a line for soft and hard machining. We have there all machines delivered by EMAG, the turning machines, hobbing machines, grinding machine, robot cell, and automation are complete supplied by EMAG. Their line cycle 90 seconds. Next example are the single concept machine on the VT, flexible, a modular system. You see there on the right side a picture with a gantry loader system and a measuring unit. So we have there aligning it on a central conveyor system. And the construction kit allowed a lot of different machining on this type. Next point, the reference for complete or realized projects. Solid shafts, complete line, machining lines, several independent single machines, machined of assembled rotor shafts and rotor package, and the hollow shafts, individual machining delivered by 2 suppliers, MEB, SSP, and polygon rotor shafts. Before we close, we would like to leave you the following message. EMAG, the point of contact of the complete process sequence. You benefit EMAG product portfolio, extensive experience in rotor shaft manufacturing, one phase to the customer, complete process from a single source, expert project management team, including construction site management and global presence. Now, Jörg, we will start with the open questions.
All right. Thank you very much, Matthias. Thank you also, Alex. Indeed, we are now going to have our question and answer session since we have nearly arrived at the end of our webinar. So in the meantime, we have received questions. Let's start with the first one. It says, what determines the flank allowance? That means the machining allowance for hard fine machining of the gear teeth. Well, I think this is a question for you and me, Alex.
Yeah.
First and foremost, I would say it depends on the module of the gear. So the bigger the module, the more stock allowance is usually required. Yeah. And of course, it is also determined by the hardening method and the distortion that is to be expected. This is actually what determines the allowance. What would you say, Alex?
Yeah, absolutely. When we want to make an example, this kind of rotor shaft we have shown before on the G250 was around 0.1 millimeter stock on the flank, so that we have only an indication.
Yeah, I think this is pretty much the same with skiving, hard rehobbing, and yeah, it's usually around about 80 microns up to 120 microns usually. Yeah, right. I think time-wise, we cannot allow another question. So, ladies and gentlemen, we have now really reached the end of our webinar. I trust you saw that EMAG offers a huge variety of different solutions all around machining of rotor shafts. And in case you should have any further question or even inquiries, please feel free to make contact to your local area sales manager, or of course, feel free to contact also us directly here. So for now, thank you very much for joining. We wish you all a nice and successful ongoing day and have a good time. Thank you. Bye.
Thank you. Bye-bye.